Hello everyone, welcome to our video lesson for today. We will be talking about the atomic models and the electronic configuration. Now, what's the connection of the atomic model with electronic configuration? So let's see. Well, before we proceed to our main topic, which is all about the electronic configuration, let us first talk about the atomic models. Okay, so the pictures above are the atomic models proposed by different scientists. Well, the first model was proposed by John Dalton in 1803. He called his atomic model as a solid sphere model. And in 1897, J.J. Thomson proposed the plum pudding model, in which the atom is composed of positive and negative particles, and the negative particles, called electrons, are embedded all throughout the atom. And in 1911, another model was proposed by Ernest Rutherford, and he named it as nuclear model. At this time, the nucleus of the atom has been discovered with the use of the gold foil experiment, wherein they have concluded that there is a dense nucleus inside the atom, and this dense nucleus is composed of a positive particle, and outside the nucleus of this atom are the negatively charged particles. And in 1913, another model was proposed by Niels Bohr, and he called his model as the planetary model, wherein the electrons are embedded outside the nucleus of the atom in definite orbitals. And inside the nucleus of the atom, there are positively charged particles, and those positively charged particles are called protons. And the latest model of the atom was proposed in 1926 by Schrödinger, and he called that model as the quantum model. Okay, quantum model, wherein the nucleus is composed of positively charged particles, which is called the proton, and the neutral charged particles called the neutron. And around this nucleus, or outside the nucleus of the atom, are the electrons. And this model here are beneficial for us to understand fully this what we call electronic configuration. Now let us proceed to electronic configuration. Now, when we talk about electronic configuration, it describes the arrangement of atoms in successive orbitals. What does this mean? Well, in the previous model that I have presented, we all know that an atom is composed of a nucleus, which is in turn composed of positively charged particles called protons, and the neutrons. And outside the nucleus of an atom are the electrons. They are particularly situated in orbitals. Okay, so the line in here are called, okay, the lines in here outside the nucleus of the atom are called orbitals. So let us see now where orbitals are really found. Now, in this particular portion here, let's say for example, I will draw another atom. This is what we call the nucleus of the atom. Okay? Let me draw again. So this is what we call the nucleus of the atom. Okay, so this is now the nucleus of the atom. And around the nucleus of the atom are the what we call imaginary lines in here. Okay. And these imaginary lines are called energy levels. Okay. So it's like here. Now, Starting from the inner core or inner portion, we have the 1s, the 2s, okay, meaning to say this is the second energy level. We have the 3s, okay, we have the third energy level, okay, and we have also the 4s, 4p, 4d, and 4f, and we have also the 5th s, okay, and so on and so forth. Now, in here, the 1s, 2s, 3s, say for example, these are what we call energy levels. Okay, so these are what we call energy levels. Now, within the energy level, okay, within the energy level, we have the, okay, within the energy level, or this what we call shell, we have the sub-levels or subshells. Okay, and within the subshells, we have this what we call orbitals. Now, orbitals are the specific, okay, specific location of electrons. Okay, so those are the energy levels, the sublevels or the subshells, and the orbitals. So let's talk about this on the next slide. Now, in the case of hydrogen here, hydrogen has a or is the smallest of all the atoms, okay? And it has an energy level which is 1, okay? So it is found in the first energy level. Helium is found on the second energy level. Sodium is found in the third energy level, and potassium is on the fourth energy level, okay? So what does this energy level tells us about? So when we say energy level represents the whole of the periods in here. So meaning to say, the elements under this are called to belong to a certain energy level. So meaning to say, this hydrogen here belongs to the first energy level, beryllium and lithium on the second energy level, okay, and so on and so forth. Now let's go back. This portion here, okay, so let's take into account this hydrogen, okay. It has only one electron, and its energy level is only 1, okay? And its sublevel is only s. Why? Because it has only one electron, and the number of electrons in an orbital is only 1. Now, when we talk about energy level, okay, it is what we call n minus equals 1. Okay, so within that energy level, we have the sub-level, which are S, P, D, and F. Okay, this is just small letter. If you can still remember that. Again, S, P, D, F. And S has only one orbital. Okay, and each orbital can occupy 2 electrons. The P has 3 orbitals, and each orbital can occupy a maximum of 2 electrons. Therefore, times 3 orbitals, so there are 6 electrons. Okay, and the D has 5 orbitals, and each orbital can occupy 2 electrons times 5, that would be equal to 10 electrons. That's the maximum number of electrons that can occupy this orbital. In the case of F, it has 7 orbitals. Okay, and each orbital has 2 electrons. Multiplied by 7, that would be 14 electrons all in all. Okay, so again, these are what we call the sublevels. Now let's take into consideration the helium. Okay, so in electronic configuration, we are using this device called Electron Distribution device, or sometimes it is called electronmnemonics. Okay, distribution mnemonics, or it is called also as diagonal line. Why is it called diagonal line? It's because of these lines in here. Okay, now let's take into account this example, or let's give some examples of the electronic configuration. Let's say, for example, we have this what we call beryllium. Okay, so we have beryllium. Beryllium, which is found here, has 4 electrons. It has also 4 protons. So let's write here 4. Okay, and its electronic configuration is like this: 1s2, and then 2s1. Okay, so how many electrons are there? There are 3 electrons. Okay, let's take into account again potassium. Potassium has 19 electrons. Okay, it's found here. So let's distribute this electrons: 1s2, 2s2. Okay, so you have 2p6, that's already 10. Then 3s2, that's already 12. 3p6, because it's 19. Okay, supposedly it's 3p6, of course. So this is 18, and we have also the 4s1. Okay, so this are 19. So let's count. 2 plus 2 equals 4, plus 6 10, plus 2 12, plus 6 18, and then these are equivalent to 19 electrons. Okay, another example. We will use the example in this portion here. So we have the boron. Okay, so we have the boron in here. Boron has 5 electrons. So if we distribute its electrons, it could be like this: 1s2, 2s2, 2p1. Okay, so this is a total of, okay, total of 5 electrons. Okay, now let's take into consideration fluorine. Fluorine has 9 electrons, so that would be 1s2, 2s2, 2p5. Okay, so that's 5 plus 4 is equal to 9. Okay, so that is how electronic configuration is written. So you'll just follow this one. Okay, so you have there 1s2, 2s2, then 3s, then 4s, okay, then 3, 5s. Okay, so that's how you follow the direction on how to write electronic configuration. Okay, so let's give you, okay, let's try more examples. Let's use aluminum. Okay, so aluminum has a number of electrons which is equivalent to 13. So that would be 1s2, 2s2, 2p6, and then after 2p6 you have 3s2. That's already 12. And then 3p, okay, 1. Okay, so if we count the number of electrons that we have distributed, that's equivalent to 13. Okay, so let's give more example. We have chlorine. Okay, chlorine is 17. So let's distribute chlorine. 1s2, 2s2, 2p6, 3s2, 3p5. So let's count. This is 10 already. Plus 2 plus 5, that would be 7. Okay, so I hope you got it already, how to write the electronic configuration. Now, let us talk about this, what we call, okay, let's talk about valence electrons. Okay, so do you have any idea what are valence electrons? Okay, so these are the, of course, electrons. That's the symbol of electron, found or located at the outermost energy level. Okay, so take note, the energy levels are, of course, here. So we have the n equals 1, n equals 2, n equals 3, 4, 5, 6, 7, okay, and 8. Okay, but of course in the periodic table you cannot yet see the 8th period. Now those are the energy levels. So let's determine the valence electrons of the different elements. Okay, so let's take into consideration that's what we call potassium. Okay, potassium a while ago has, of course, 19 electrons. So that would be 1s2, 2s2, 2p6, 3s2, 3p, okay, 10, 12, okay, 3p6. So this will be 12 plus 6, that would be 18, then that would be 4s2. Okay, so truth to the matter is that potassium here belongs to the fourth group. Okay, so in here you can see the energy level or the period where a certain element belongs and is grouped. Okay, so here we have the fourth energy level, so therefore it belongs to period number 4, and its valence electron is only 1. Okay, so ayan. Valence electrons are the outermost electrons. In the case of potassium, its outermost electron is only 1. So let's give more examples using other elements. Okay, let's try nitrogen 7. So that would be 1s2, 2s2. Okay, again, nitrogen 7, that would be 1s2, 2s2, 2p1. Okay, so that, I know, 2p3. Okay, so that would be 7. 2 plus 2, 4 plus 3 equals 7. So the valence electron of nitrogen is, of course, you got to add this 2 here because they both belong to the same energy level. The valence electrons are, of course, 5. That is the reason why nitrogen belongs to group number, and it belongs also to period number 2, as evident in here. Okay, so that is how to get the valence electrons of elements. Okay, so another example, last example, we have the chromium, which has a number of electrons equivalent to 24. Okay, so that would be 1s2, 2s2, 2p6, 3s2, 3p6, that would be 18. Okay, and then 3p6 is 4s2. Okay, and then 4s2, and of course 3d4. Okay, so let's count. This is 2, 4 plus 6, 10 plus 2, 12, 18, 19, 20, and the last one is 4. Okay, 3d4. So in here, that's what we call 3d4. Okay, but if we will determine the valence electrons of these elements, we have the highest main energy level is 4, therefore its valence electron is 2. Now this is not the outermost electron. Actually, if we will draw this into an atomic model, it would be like this. Okay, so this will be n equals 1, n equals 2, n equals 3, and lastly we have n equals 4. Still, the fourth energy level is the place where valence electron is found. Okay, I hope you know already how to get the valence electron. Okay, so